Section 5.2, we're going to talk about slope. And in section 4.3, we were talking about linear relationships and consequently talking a lot about rate of change, because a constant rate of change is the key characteristic of a linear relationship. And in that section, we saw that we could look at the rate of change as the slope of the line that describes the rate of change when you're looking at that graph. So in this section, we're going to explore slope in more detail. Activity 1, we're going to look at the rate of change, and we're going to look at slope for a particular example here that involves Sam saving money that he earns from babysitting, and the graph is shown below. Let's take a look at the graph down here. All right, so with the graph, it's always good just to take a minute, look at what does the horizontal axis represent? What's the scale? What does the vertical axis represent? What's the scale? What's the graph about? All right, let's go look at our first question. What is the rate of change of Sam's savings with respect to time spent babysitting? Include units in your answer. You remember how to do rate of change from a graph? Right, we want to look at the change in the vertical divided by the change in the horizontal. So if we start here at 0, 0, and we draw these little stair steps, the change in the vertical looks like 10, which would be dollars, and the change in the horizontal is 1 hour. Right, up $10 over 1 hour. Change in vertical over change in horizontal. Let's go write that down up here. All right, so our rate of change is an increase of $10 divided by a horizontal increase of 1 hour. So we included the units in our answer. That's great. So if we wanted to interpret this, the $10 is how much Sam is saving, not how much he's earning, right? Let's go down and look at that. Oh, it says it up here, doesn't it? It's how much he's saving. He may be earning more per hour and only saving $10, right? So we don't know if he's saving all the money he's earning or not. So I think we could safely say here that Sam is saving $10 for every hour he's babysitting. For each hour he's babysitting, or something like that, okay? Excellent. B, if you move from the point 220 to the point 990, what is the horizontal change and what is the vertical change? Draw these changes on the graph and then complete the table below. Let's go take a look at that. 220 to 990. Let's erase this. Okay, so we're going to go from the point 220, which is right here, to the point 990, which is right here. Okay, this is going to be a challenge to draw a nice straight line for you. Pretend like that's nice and straight. And then across this way. All right, so what does the vertical change represent here? How much is that? It's definitely a change in money. Right, so this point 220 represents $20, and we're going all the way up here to $90. So if we move from $20 to $90, that's a $70 increase. All right, let's look at the horizontal change here. This horizontal change. So this value right here is 2 hours. And then over here we have 9 hours. So if we're moving from 2 hours to 9 hours, that represents a 7-hour increase. All right, let's go fill in our table. So the horizontal change was 7 hours, and the vertical change was $70. And so the interpretation would be we have an increase of babysitting time of 7 hours. Maybe he got a job of 7 hours of babysitting. And we have an increase of savings of $70. Maybe an increase in savings would be a better way to say that. Okay. C says, imagine walking uphill along this line from the point 220 to the point 990. Right, so we're walking up this line, Up we go. Should I draw a little stick figure? Probably not. Oh, why not? That would be fun. Here we are. We're walking. We're walking up this line. We define the slope of the line segment between these points to be the ratio of your vertical change to your horizontal change. This looks a lot like rate of change, doesn't it? Slope is the vertical change over the horizontal change. What is this value? How does your value compare to your answer in part A? All right, so our slope is the vertical change. So for us, that was, for this example, using these 2 points, walking from this point to this point, was $70. And the horizontal change was 7 hours. So we'll divide that by 7 hours. And what do we get when we divide 70 by 7? Right, we're going to get 10. And it's going to be dollars per hour, which is exactly what we got from part A. All right, let's look at D. Now choose 2 other points on the graph and compute the slope of the line segment between them. Draw the horizontal and vertical line changes on the graph. What do you notice? All right, so I want you guys to do this on your own. I want you to come back to this graph and pick 2 other points. There's lots of points to choose from here. Don't pick 0, 0. Do something more exciting. All right, pick 2 other points. Don't pick 0, 0. Pick 2 other points here and draw the vertical and horizontal, and then calculate the vertical change divided by the horizontal change and see what you get. And start the video when you're done. All right, I don't know what you picked, but I'll just do something that maybe people wouldn't pick. I'm going to go from 770 over here to 10,100. All right, so I went from 70 up to 100. That's $30. And then we went from 7 hours over to 10 hours, so that's 3 hours. So let's go over and write the vertical change divided by the horizontal change over here. So the vertical change in the example I used was $30, and the horizontal change was 3 hours. So 30 divided by 3 is $10, and my units would be $10 per hour. What do you notice? We got the same thing. All right? What can you say about the triangles that result from adding the horizontal and vertical changes in part C and D? This question came up also in section 4.3. Let me put that other triangle in that went from 220 to 990, the one that I erased. Let's put that back in. All right, what can we say about these 2 triangles here, the blue triangle and the pink triangle here? Oh, it's hard to draw straight lines with this. Okay, there we go. You remember what it's called when triangles have pretty much the exact same shape, but they're different. Not pretty much. They have the same shape, the same angles, but they're different sizes. Do you remember that? Like this pink triangle is a shrunken version of the blue triangle. It's called similar, right? The triangles are similar. They are similar triangles. I don't remember what section we covered this in, but it was in an earlier section. And we know from similar triangles that the sides are proportional. In other words, if you divide the corresponding sides, they'll have the same ratio. I'm going to run out of space here to write proportional. Sides are proportional. And that's really what we're seeing here, right? We have a side of 30 divided by a side of 3, and that's going to be proportional to a side of 70 divided by a side of 7. So those ratios are equal, which is $10 per hour. And that would be true for any triangle that we picked. You know, mine was 30 over 3. You probably had something else. And that's the slope. All right, so here we're defining slope of a line. Suppose that quantities x and y vary linearly. We define the slope of the line that describes the linear relationship denoted by the letter m as follows. And there's a little subnote or a footnote about why do we use m to talk about slope at the bottom of the page if you want to investigate that. So slope, defined by the variable m, is the vertical change divided by the horizontal change, or the change in y divided by the change in x. As we saw in activity 1, the slope of the line is equal to the rate of change of y with respect to x. Now, this is kind of the important part here. Well, it's all important, but this is an interesting part. Since the vertical and horizontal changes are proportional, because of the similar triangles, you can use any 2 points on the line to compute the slope. The ratio is always the same. You can use any 2 points on the line to compute the slope. Let's look at activity 2. We're going to compute some slopes. Find the slope of each line segment in the grid below. Each box in the grid has dimension 1 by 1. All right, so remember you're doing change in y over change in x. Why don't you pause the video and find the slope for each of these line segments and then start it up when you're done. All right, let's look at line segment number 1. I'll do it like that. So the slope is the change in y, so that's going to go up 3. Oh boy. Okay, that's better. Up 3 over 2. Up 3 over 2. That's the slope of 1. Okay, let's go to line number 2. Let's go. I'm going to do dotted lines. There we go. It's up 1 over 2. So the slope is up 1 over 2. So the slope is 1/2. Another way you could look at a slope of a half, this is a little bit weird, but I'll show you. I could go up a half over 1. Up a half over 1. Up a half over 1. Or you could go up 1 over 2. That's basically the deal with the similar triangles. All right, let's look at 3. So 3, if I start here, I'm going to show you 3 in 2 different ways, okay? If I start here and I do my vertical change going down, so I'm going down 2, so that's -2, and then to the right 2. So my vertical change is dropping. I'm having something is decreasing here. So my slope is -2 over 2, which -2 divided by +2 is -1. So we could have also done, and maybe some of you did this, down 1 over 1 to this point. Down 1, right 1. Down 1, right 1. Okay, so another way we could have looked at it, remember we were talking about walking up a hill, we could go from this point to this point, and we could go up 1 and then left 1. But from the standpoint of looking at change, we usually are reading a graph from left to right to see what happens over time. But usually over time, it could be over other things as well. But this does work if you look at it this way, right? If you did it this way, you'd have a vertical change of +1 and a horizontal change of -1, and 1 divided by -1 is still -1, so you will get the same answer. All right, let's look at these last 2, which are a little bit tricky. Let's look at 4. They're a little different. So if I move from this point to this point over here, I don't have any vertical change, right? I'm just moving 1 to the right. So if I write the slope, I say I have 0 vertical change over 1 horizontal change. And 0 divided by 1 is 0. So when we have a horizontal line, the slope is 0, indicating that there's really no change in the whatever the vertical axis is representing. Like if Sam wasn't saving any money over some months, there'd be a horizontal line showing no change in his savings. All right, let's look at 5. So 5, if we go from here to here, we have a vertical change of 2, right? We have a vertical change of 2, but we have no horizontal change. All right, what is this value? Well, if you take out your calculator and you punch in 2 divided by 0, you're going to get an interesting response from your calculator. This calculator has a particularly interesting response. It's very verbose. 2 divided by 0 equals, cannot divide by 0. Your calculator probably says error or I don't know, something like that, but it certainly is not giving you an answer because there is no answer. We cannot divide by 0. Why is that? Let's talk about that for just a second. Well, before I do that, so then the answer to this would be, we would say the slope is undefined, or sometimes we say there's no slope. Now, for a vertical line, we're always going to have no slope or undefined. For a horizontal line, we're always going to have a slope of 0. And the way that I remember this, of course, we could go back and do rate of change. When I think of slope, I think of skiing, right? So I could ski on 4 as like cross-country skiing. It just has a slope of 0, but I could still ski on it. I can't ski on 5. I would be undefined if I skied on 5. That's a little thing that I used to use to remember it. Okay, now let's talk about why we can't divide by 0. Let's just talk about that real quick, dividing by 0. Let's think about what division means. So if I have something like 8 divided by 2, it's literally asking me like how many 2's would I have to add together to get 8? Right, how many 2's? And it would be 4 2's, right? 2, 2. It's multiplication is repeated addition. You could think of division as repeated subtraction also, right? You could think of it as how many 2's would I have to subtract in order to get to 0? Since multiplication is repeated addition, how many 2's? Well, I'd have 1, 2, 3, 4 2's I'd have to subtract in order to get to 0. And then you also have this relationship that 4 times 2 has to equal 8. Right, so that's division. Now let's think about what if I was dividing 8 by 0. If I was dividing 8 by 0, well, now I'd be asking the question, how many zeros would I have to add together? How many in order to get 8? There's no amount of zeros I can add together to get 8. It's never going to happen. What if I think about it as repeated subtraction, right? How many zeros would I have to subtract from 8? To get to 0. I could do this forever. I'm never going to get there, right? There's no answer. I'm never going to get to 0. And lastly, you could also think, whatever this answer is, these two numbers would have to multiply together to give 8. And there is no number times 0 that will give you 8. So that's 3 different ways to think about division. And no matter which way we think about it, we can't get an answer when we're dividing by 0, right? There is literally no answer. All right. Let's go look at the next example here. So we saw in the previous example that we had some positive slope, some negative slope, 0 slope, and undefined slope. Those are really the 3 options. Let's take a look over here again. So we had number 1 and number 2 had a positive slope. Number 3 had a negative slope, a negative rate of change, right? Something is decreasing, savings, temperature, something, whatever, some application that might help you think about it. We could have a 0 slope, which is a horizontal line, and a vertical slope, which is undefined. So what I want you to do here is just sketch a graph, just a generic graph of some lines that would meet these criteria. Go ahead and pause the video and start it up when you're done. All right, well, there's lots of different answers for this, but for a positive slope, your line should be, moving upwards as you go from left to right. It could look like that. It could look like that. It doesn't have to start at 0, 0 to be a positive slope. Most of the stuff we've done has gone through 0, 0, but it doesn't have to. Right? It could be up here. Negative slope, maybe something like that. It could be very steep like that, or it could be kind of flat like that, but as long as it's going downhill, that's a negative slope. Zero slope has to be a horizontal line, and it could be placed anywhere here. Undefined slope has to be a vertical line, and you could place it anywhere you want. Now, roofs are use this idea of slope, and they talk about pitch. You lived in a house once that had a 12-12 pitch. It was very steep. So in this example down here, this house has this roof has a 5-12 pitch. And when you talk to roofers, they'll talk about pitch in terms of something over 12. So this roof of a 5-12 pitch means for every 5 inches of vertical increase, the roof has 12 inches of horizontal run. And it's always over 12. So sometimes there's like a 6-12 pitch or a 9-12 pitch, and like I said, mine was a 12-12 pitch. So let's have you guys draw a picture of a 6-12 pitch. Maybe just extend this picture. That might be a good way to do it. There's lots of space here, but we're going to answer the question, which one of these roofs is the steepest? So if we were drawing a 6-12 pitch, we could just use this 12, and instead of 5 here, we would add another inch, right? So we could do like something like this. That would be 6 inches. And then we'd go 12. So a 6-12 pitch roof would look like that. And we could extend it over here as well. Let's see, we'll try to draw this. There we go. Okay, draw the 9-12 pitch. Maybe add that on to our diagram here. We'll do it at the same time. Okay, so 9-12, I'm going to have to add like another 3 inches. You could get a ruler if you wanted to, but this isn't to scale. So we'd have to add another 3 inches up here to make this whole thing 9 inches. And then our roof would look like that. So which one of these roofs would be the steepest? Right, the 9-12 pitch, right? The 9-12 pitch would be the steepest. So because we have a vertical increase of 9 inches over a run of 12. So the smaller the vertical increase over the same run of 12 inches, horizontal change, when I'm using the word run, I'm talking about horizontal change. The smaller that vertical increase, the less steep the roof is going to be. And like I said, mine was a 12-12 pitch, so that was pretty steep. Let's look at one more example here. Suppose you're driving down the road and you come across this sign. Describe what you think this sign is telling you. All right, pause the video and write a few sentences about that, and then start it up when you're ready. Well, hopefully you said something like there's a downhill coming up, and maybe some of you use the word grade. Right? You'll see this sometimes when we're talking about roads and steepness, and we would call this a 20% grade. And really what it's describing is, let's say we have a road and that road is going downhill, okay? It's losing elevation. So a 20% grade would mean that you are going to drop 20 feet or 20 units. It wouldn't have to be feet, but usually when we're driving we think of feet or meters, something like that, over 100 units. Let's put units. Now it's probably not going to be miles because that would be a very long road. You know, you're probably not going to have this uniform steepness over that distance of 100 miles, but so I think feet is a good way to think about it. You would drop 20 feet of elevation for every 100 feet that you're moving along the road. So I think we've answered question B here. If you're driving up this hill and move forward 100 feet, so when we talk about forward 100 feet, we're really talking about moving this direction 100 feet. Okay, like north, south, east, west 100 feet, not up the grade, because this value, the length of this road right here is not 100 feet. That's really important, and we're going to cover that in a section in this unit. We're going to learn how to find this distance right here, but it is not 100 units. Okay, so when we talk about moving forward 100 units, we're talking about moving in the direction that you're going, whatever that is, north, south, east, west, northeast, whatever. Okay, so if we move forward 100 feet, what is your resulting change in elevation? Well, if you're going uphill, then you're going to have an increase in 20 feet of elevation for every 100 feet you move forward. Increase of 20 feet of elevation. I kind of took for granted here that you saw the connection between the 20% and the 20 over 100, but maybe I should take a second and talk about that. If we looked at the slope of this line, it would be the vertical change, which is 20 units, over the horizontal change, which is 100 units. Okay, so 20 divided by 100, if we put that in decimal form, would be 0.2, and since these are the same units, feet, whatever, those would cancel out, and 20 divided by 100 is 0.2 in decimal form, and if I change that to percent form, I get 20%, right? 20 over 100 is 20%. So when we have a 20% grade, that means 20 over 100, so we're going to have a change of 20 in the vertical and a change of 100 in the horizontal for our slope. All right, part C, if your elevation were to increase by a mile along this hill, now we're going to go to miles, how many feet would you have moved forward? Okay, let's draw a picture of that. If your elevation would have increased by a mile. Okay, so 1 mile. How many feet would you have moved forward? So we're trying to find that distance there. And this is the road. All right, this is the road. If you want to pause the video and think about this one, go ahead and do that. All right, let's do this by scaling. So remember that these slopes, we could pick any 2 points on the line, and we know our slope is 20%. That grade is the slope, which is 20 over 100. But we want to know, what would this value be down here if the vertical change is 1. So we really want, let me make this a different color here. Let's make this yellow. We want this value up here to be 1. And then whatever the bottom value is here, that will be our answer. So how could we scale this down so that the top number was 1? Well, we could just divide by 20, right? So if we divided by 20 on the top and the bottom and scaled this down, we would have the fraction 1/5. 1/5 is also 20%. It's also 20 over 100. So that would mean that if I had a vertical change of 1 mile, I would have a horizontal change of 5 miles. Awesome. So this would be 5 miles. Now let's go back and read the question. The question was, how many feet would you have moved forward? So now we need to convert our 5 miles into feet. So if you don't remember, you're going to have to look up the conversion factor for feet to miles. And that was 5,280 feet in every 1 mile. So there's our unit analysis that we learned how to do before, right? And so we can cancel out those miles, reduce those. Miles divided by miles would be 1, and we'll take 5 times 5,280, and we'll have our answer. All right, looks like 26,400 feet would be your horizontal distance, or how far you moved forward in a directional sense. All right, well, we'll be talking about slope more in the next activities.